welcome to nuclear chemistry. In nuclear chemistry, we have to think of stable and what are called radioactive isotopes. So, looking at this question here, what do you think would be the isotope of copper? Answer the question in your head. Let's see what you think. Could this be an isotope of copper? No, that's gold. Got number 79. And what about this isotope of copper? 29, that's the atomic number of copper, maybe. This one, 29. This one, 29. This one, 28. Could it be copper if it's 28? Nope, wrong element. This one, 29. So here we've got a number of different isotopes. A, D, E, and F. Now, if you look at these isotopes, which of these may not be possible? Well, this one looks a little weird. 34 of them. 34 for the mass. That's protons plus neutrons. 29 for the protons. That means this one's only going to have 5 neutrons. Seems a little bit low. So we're going to be looking at today that ratio of the protons to the neutrons and how you know whether E, F, D, or A are stable isotopes of copper. So what types of isotopes do the various elements have? We'll be able to look at a graph, describe nuclear composition, and look at a stable and a radioactive isotopes. Now, things you need to know, the graph of the naturally occurring isotopes gives us an idea of how many different isotopes of the elements are found in nature. Remember, the periodic table only gives us 2 of those, but we know we can have between 2 and 10 on many different substances. The words atom, isotope, and element are interrelated. When we talk about the periodic table of elements, we could also talk about the periodic table of atoms if we're just talking about a single atom. Also, the definition of an isotope tells us that the isotope here, isotope is related as well, so it probably should be called the periodic table of isotopes because it's the most abundant isotopes that are found on the periodic table. The other ones, not the most abundant ones, again, the ones that are off of the average, or not closest to the average, those isotopes here are different than the ones on the periodic table by the number of neutrons. All atoms have at least 1 neutron for every proton in the nucleus, nearly all of them. One exception is hydrogen, which we'll look at. This here is a graph of the band of stability. You'll notice it compares neutrons to protons. So if we have an element on here, such as copper, and copper, if we look on the periodic table, copper is number 29, and it's got a mass of about 64. And that's the most abundant isotope of copper. Again, we saw there's a bunch of different ones. Some of them might be possible or not. So if we look at this and we go, okay, 29 and 64. 29, I know that's the number of protons. So I go here, 29, up here, and then I go, okay, 64. So 29 and 64, that's going to be like up here. Wait a minute, that's not even on this band of stability. It's not even on the graph. What did I do wrong? Oh, that's right, 64 minus 29 gives me the number of neutrons. So 64 minus 29, carry the 1, add the 6, that's what, 30, 35? 35 neutrons. So if we look here at this and we go, okay, now I go 29 to 35, that should be right about there. But there's nothing even there. So with copper, we've got these 2 isotopes there of copper, and we would think 64 is the most likely, but in nature, that's not what happens with copper. If we look at the graph narrowed down, we can see here that the black ones, they represent the most abundant isotopes, the gray ones are other isotopes, and the other ones are radioactive. As you can see here, down near the bottom, most of them lie on this line. This line is a 1-to-1 ratio between neutrons and protons. It's got a slope of 1, as you can see. It goes up, up 5, over 5, so on. As you go further up, you'll notice that this band of stability here, this is called the band of stability, the slope of it increases. It gets greater than 1-to-1. There's more neutrons per protons. And as we go further up to the higher part of it here, we can see that the slope continues to increase as we go up, and then there's a little skip. And then we've got this section here, which is called the island of stability. And this island was first supposed, there's a gap here actually, and then these elements here, these are some of the ones that are almost all, except that one, almost all created by humans. Many isotopes have more neutrons than protons. Isotopes of elements after bismuth are all radioactive. So anything after 84, it's radioactive. That's a radioactive zone we played with in the game. Some elements have a naturally occurring radioactive isotope. Other ones, you can create a radioactive isotope, and we'll be looking at how that works. Radioactive isotope is any isotope that has an unstable nucleus and decays over time. The amount of time that it takes it to decay is what we call the half-life. Now, what types of isotopes do the various elements have? Okay. It has between 1 and 10 isotopes. Neutron to proton ratio is an important factor, and we'll be looking at this factor determining the stability of an isotope. The ones with small masses, it's about 1 to 1. The ones with larger masses, about 1.5 to 1 or 3 to 2. Some elements have isotopes that are radioactive, and these radioactive isotopes are unstable and they decay over time. So if we look back and use our chart from lesson 14, we should be able to determine how many neutrons you would need to make a stable element with 79 protons. Please answer this question. Bring this to class. Now, in our nuclear quest game, we were looking at what are nuclear reactions. So we were able to explain these things here from what we did in class as well as what we're learning now. So, types of radioactive decay. In class, we learned about a few things, okay? We knew that there was alpha, we knew there was beta, we also knew there was gamma. We also know there's a process called nuclear fission and nuclear fusion. All the cards included those processes. This is the international sign for radioactivity. An alpha particle is a particle that leaves, again, the nucleus, and it's written as a 4/2 with the alpha sign. Beta particle has this characteristic, 0/-1 beta, and a gamma particle is often written a gamma sign as a 0/0. Positron emission, we won't be looking and testing on that in Chem 1-2, but we will look at how that works, and electron capture as well. These are all called radioactive decay processes. In alpha decay, you have a nucleus here, like uranium-238. This nucleus here is unstable, and it spontaneously breaks up into a thorium nucleus and an alpha particle, which we know now is 4-2, and something that has an atomic number of 2 on the periodic table. What element is that? That's helium. So this can be another way of showing the helium particle. It also releases a gamma ray, which is energy released in the form of gamma radiation. Beta decay looks similar, but it's releasing a beta particle. The unstable nucleus, oh, wait a minute, the mass, the atomic number goes from 6 to 7. That seems a little weird. The beta particle is released, and a gamma ray is released. Beta particle, formula looks like this. Can also be written as beta particle. That's the other one you should memorize. Alpha particles and beta particles often get emitted, and this is called beta decay. Here's a summary of some of the processes for radioactive decay. Alpha emission, here's the symbol. The change in atomic number, it's -2. That means it goes back 2 places in the game we played. Change in mass number, -4. Change in the number of neutrons is -2. If you add -2 plus -2, you get -4, just as a hint. So if you add those two together, you get the change in the mass number. A beta emission is looking like this. The little e stands for an electron. So it's an electron that's leaving the nucleus. And +1, -1, and 0 change in mass. In a gamma emission, you got no changes in mass or in charge. Penetration power, alpha particles here. Alpha particles here, they travel and they get blocked by a piece of paper. Beta, aluminum or aluminum foil. And gamma particles can pass all the way through and into lead, and the lead has to be incredibly thick to block the gamma radiation, or a large piece of concrete. Nuclear chemistry is the study of changes to the nucleus. A nuclear reaction, this process involves changes to the nucleus of an atom. Radioactive decay is a spontaneous process by which an atom emits radiation or a particle from its nucleus to become more stable. Fusion is the joining of two nuclei together, and then fission is the breaking apart of an atomic nucleus into two. These two words, fusion and fission, often are confused. One way I remember this is fizz or fizz. This happens every time I open a container of soda. Sometimes I drink more soda than I should, but the container of soda, when you open it up, it opens up and it fizzes. One of the things that happens is when you open that container, the bubbles actually form in the solution. The solution, as it's pressurized, is, again, your soda solution doesn't have those bubbles that form. When you open it, you release that pressure, the bubbles form and they separate from the solution. So we've got a very easy way of picturing it. You've got the solution, you open it, and then the bubbles form. It fizzes, and the bubbles leave the solution. Just like in a nuclear reaction, we have one thing breaking up into two smaller things. Okay? Fission often can be referred to as a decay process, but usually fission is when something is intentionally done to cause the atomic nucleus to split apart. So decay and fission are so related. Fusion are two things fusing together. Changes in the nucleus of an atom can change the identity of an element. You've got an alpha particle, you've got beta particles, and then you've got gamma rays. All of these need to be understood vocabulary to talk about nuclear chemistry. Nuclear changes frequently involve the transfer of large amounts of energy. We've got alpha decay. This is a reaction when an atom emits an alpha particle. The atomic number decreases by 2, mass number decreases by 4. Beta decay is when a neutron changes into a proton and the atom emits a beta particle. Beta particles are also called electrons. So how does this work? Here's the symbol for a neutron. It's got a mass of 1, it's got 0 charge. This neutron breaks apart into a proton, which has, again, a mass of 1 and a charge of 1. And this proton is composed of a hydrogen nuclei. And the other thing that's emitted is a beta particle. A beta particle has -1 charge and is equivalent to an electron. It's an electron leaving the nucleus. So if we add these up, if we look at the numbers, 1 equals 1 plus 0, does that make sense? 1 equals 1 plus 0, yep. And on the bottom, 0 equals 1 minus 1. Aha, so the neutrons in the nucleus, when they become unstable, that's when you can get beta decay. Now, nuclear reactions, we've got alpha, we've got beta, we've got gamma. Those are the three we focus on. Nuclear fission involves a single nucleus breaking apart. Fusion involves two combining together. This happens in extremely hot places like the cores of stars. As we saw, the best card to get in the game, one of the best cards, was the nuclear fusion card. And if you could get the supernova, this is how many of the heavier elements were believed to be formed somehow in a supernova explosion, and those elements then collected together in some way. The iron of the Earth collected together and formed our Earth as we know it. So in our sun is not a very warm, a very hot star. The reactions that are taking place here are two nuclei coming together like hydrogen, coming together and fusing together to make helium. These are some characteristics of some different types of radiation and the amount of penetrating power of these types of radiation. If you look at decay...
Cobalt, carbon-14 spontaneously emits beta particles from its nucleus. Since beta particles are attracted to the positive placed on a radioactive field, they must be negatively charged. In fact, beta particles are electrons that are formed and then emitted from the nuclei of certain radioactive isotopes. In the decay process, a neutron is converted to a proton and a beta particle. A carbon-14 nucleus contains 6 protons and 8 neutrons. During beta decay, spontaneously emits gamma rays from its nuclei. Since gamma rays are undeflected by an applied electrical field, they have no electrical charge. Gamma rays are very high-energy electromagnetic radiation that have no detectable charge or mass. A cobalt-60 nucleus contains 27 protons and 33 neutrons. When a gamma ray is emitted, the number of protons and neutrons in the nucleus is unchanged. The half-life for this process is 5.26 years. This means that half of a given sample will undergo this process every 5.26 years. Radon-222 is being formed continuously in our environment by decay of uranium-238. Radon, being a noble gas, is chemically non-reactive. Therefore, it is not trapped by chemical processes in the soil or water, and is free to seep up from the ground and into homes. Radon spontaneously emits alpha particles from its nuclei. Since alpha particles are attracted to the negative plate of an applied electrical field, they must be positively charged. A radon-222 nucleus contains 86 protons and 136 neutrons. During alpha particle emission, a particle composed of 2 protons and 2 neutrons is emitted. An alpha particle is equivalent to a helium-4 nucleus. When an alpha particle is emitted from a radon-222 nucleus, a polonium isotope, polonium-218, is produced. Since an alpha particle contains 2 protons, the atomic number decreases by 2, from 86 to 84. An alpha particle has a mass number of 4, so the mass number decreases from 222 to 218. The polonium-218 isotope produced is unstable, and therefore undergoes further radioactive decay. Both alpha and beta particles are deflected by an applied electrical field, while gamma rays are unaffected. Also note that alpha particles are deflected less by the applied electrical field compared to beta particles due to their higher mass. An alpha particle composed of 2 protons and 2 neutrons is approximately 7,000 times the mass of a beta particle.
So with the formation of elements, we're going to look at how elements can be formed. So if we look here at some of these patterns, you should notice some patterns in the fusion reactions that you think all can be created on Earth. So one pattern you might see, as you look at these, is here all of them produce energy. All of them are producing energy. The other thing you might see is you start out with 2 small things and put them together into nuclear fusion. And you take one of these things, add one of the small heliums again, and keep going and going and going. So what you can see is if this process can continue, you're going to get elements, goes from 8 to 12 to 16, or 4 to 6 to 8 based on their atomic numbers. You can see this is an even pattern, and this pattern here is how elements on the stars are formed. And now they release large amounts of energy. So how are new elements formed? We're going to look at how elements are formed through nuclear reactions and nuclear equations. Okay? We're going to look at alpha decay with the helium nucleus and beta decay emitting an electron. Nuclear fusion involves the joining together, and fission is the breaking up. Nuclear reactions change the identity of an element. Chemical reactions do not, but nuclear reactions do. Nuclear fusion produces bigger or heavier elements from lighter ones. So here's an example of some nuclear reactions here. So for this first one here, this is uranium. And if we take uranium symbol and we look at the periodic table, grab the periodic table here, we look, uranium has an atomic number of 92. Okay? Change this to color. There we go. So uranium's atomic number is 92. Its mass number on the periodic table is 238. Now there are multiple isotopes of uranium, So let's say we chose 238 as one of the isotopes that happens to be radioactive. Okay? If we look at this reaction here, you start with uranium. Uranium, because of its weight and because it's heavy, goes through alpha decay. So if you're told you have a uranium nuclei going through alpha decay, that means that the particle emitted is going to be an alpha particle, or 2He. The second product is going to be the daughter isotope of this parent. So this is called the parent isotope, this is called the daughter. So you've got 238, losing 4 is going to be 234. And then you've got 92 minus 2, that's 90. The isotope here, you look on the periodic tables, number 90, the symbol is Th, or thorium. That's an alpha decay reaction. If you have a beta decay reaction, barium is one particular element that can undergo a beta decay reaction. Barium here has an atomic number of 56 and a mass number of approximately 137. You might be told what isotope you're using, usually that's the case. But let's say we're using the most abundant isotope of barium. It happens to be, if it is unstable, what would happen? So we take barium 137, we lose a beta particle, it's called beta decay. So here we need a beta particle, and then our other product is our daughter isotope, is 137 minus 0, which is 137, and then 56 minus 1, but it's minus 1, because it's a minus 1, 56 minus 1, and that equals 57. The atomic number goes up by 1, as we would predict from beta decay, and that gives us the element lanthanum, La. Now, another example of a nuclear reaction is a fusion reaction. So this would be an example of a fusion reaction here, or even sometimes it's called an alpha particle capture, where you have a helium being captured by being collided with and connecting to a chromium to make an ion. So we can fill in the information we know right now. This is 26. This is 26 plus 2, hopefully. I'm sorry, not 26 plus 2. This has to be 24 for the math to work. And then the mass number, if we assume we're doing the most stable isotope of chromium, which again, if we're told that would make it easier. 52 plus 4 is 56. And so this makes iron here with the most abundant isotope of iron here. So this is an example of a fusion reaction that can happen. In alpha decay, we have an alpha particle is ejected from the nucleus. Okay, it's a positively charged particle. These are the equations, and you'll notice that the positive charge is included in the equation itself, showing the representation. However, it is included as a 4-2He. Alpha decay is limited to heavy radioactive nuclei. Alpha radiation is a picture of it, and the parent and daughter nucleus idea. In beta production, beta decay, the electron is ejected from the nucleus. The beta emission converts a neutron into a proton. That's why the atomic number, or the mass number, I should say, you'll notice here, there's mass number. Let's see here. The mass number increases by, the mass number stays the same, and the atomic number increases by 1. Here's a picture of beta radiation, where the electron is emitted. Another particle, subatomic particle we won't be talking about, is called an antineutrino. It also can be emitted in this process, and these are things that often physicists look to measure. Gamma radiation, this is when energy is emitted if there's excess energy following the decay and emission of other particles. So here you've got the thorium going to PA, and then the PA is an excited daughter nucleus that emits that photon, which is a gamma radiation. So the gamma photon is released, and that's energy. Gamma ray production. Gamma radiation is a high energy electromagnetic waves. On the equation we drew out, we did not include the two gamma rays. but those are also produced in alpha decay. Gamma rays are massless and do not by themselves change the nucleus. Balanced chemical equations, here are some steps, if you like, step by step. The first thing is you need to conserve the mass number. The sum of the protons plus the neutrons in the products, which is on the right side, must equal the sum of the protons in the reactants, which is the left side. So in this one here, 235 plus 1 equals 138 plus 96 plus 2 times 1, because you've got the 2 in front of the neutron. You must conserve the atomic number Z, or nuclear charge. So the same thing, left and right must be equal. So 92 plus 0 equals 55 plus 37 plus 2 times 0, because of that big 2 in the front. Here's an example of a nuclear equation. This is uranium being bombarded by a neutron, which can make it unstable, and it breaks up into barium, krypton, and 3 neutrons. And we'll look at this one in particular. This is a nuclear fission reaction that's started by a neutron being added. But looking at the nuclear equation, you got to match them up, make sure it's balanced, and you're good to go. Here's another one. You don't know what's going on the right side, so it's 226 equals 4 plus something. You should see now that would be 222. 88 equals 2 plus what? 86. That's where you get the numbers, and you get the symbol. Here's another equation. It's got something missing. You set it up. 95 must be the atomic number. The mass number. You add up the bottoms. 39 must be the atomic number. That's ytterbium. So to check in, you've got 212PO decays by alpha emission. I'd like you to write the balanced nuclear equation for the decay of 212 polonium. Please bring that to class. Now, in the band of stability, this here is what we looked at earlier. One of the things you may notice in the band of stability is the decay happens to return the nucleus towards the band of stability. So the decay happens for it to be towards the band of stability as it changes to a different isotope. The most stable nuclide is iron 56 on the periodic table. If Z is greater than 83, the nuclide is radioactive. So that's, again, we said that before, atomic number. If the ratio of N over P is too large, it's larger, it goes through beta decay. If it's too small, it goes through positron decay or electron capture. And then on the heavier ones, that's where you get the alpha decay. Up here at the top, you get the alpha decay. So that's where you get the alpha decay here. Beta decay happens down here, and there's a positron emission and electron capture. Now, predicting the mode of decay, if you got a high N over P, and it goes beta decay, low N over P, it goes through positron decay or electron capture, and if you're above 83, it tends to go through alpha decay. And these are general properties. A nuclear chain reaction, like we saw earlier, when you combine a neutron to a uranium-235 nucleus, it breaks up into its products, barium-141, krypton-92, and 3 more neutrons. If you have a sample of uranium-235, that one neutron makes a chain reaction where 3 more neutrons are produced. They get 3 more uraniums. Those uraniums break apart. Every time it breaks apart, energy is released. Energy, 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 energy. And this is how a nuclear reactor can be powered. It's based on controlling that energy. Oftentimes that energy is put into water, and the water is boiled to turn a turbine to create electricity. That's how we get electricity from a power plant. But this is called a nuclear chain reaction. It happens to be called fission because the nucleus, even though it's colliding with an N, is breaking apart into smaller particles. Nuclear fission is a process that releases enormous amounts of energy. You can produce a great deal of energy with a chain reaction. So you set up a chain reaction that produces great amounts of energy. Here are 3 isotopes of hydrogen. You'll notice the big difference here is the number of neutrons. And this is what happens with tritium. Tritium goes through beta decay. It is not stable with those 2 extra, with the mass number of 3 and the 2 extra neutrons. So what you can see here is you've got the 2 neutrons spontaneously, one of them spontaneously breaks apart and changes from a neutron into a proton, and an electron is emitted. So this is a good example of beta decay. The rate at which nuclear decay happens is completely random. The rate is independent of temperature, pressure, concentration. Each radioisotope has its unique decay rate, and decay is measured as what's called a half-life. So you start with a certain amount of a sample. When half the sample is gone, that's what is called the half-life period. So the time for half the sample to decay doesn't just disappear, it changes into another isotope. And sometimes that isotope can be radioactive, and you can keep going and going and going and going. So here's some uses of isotopes. Some of their uses, a lot in medicine, also in geology, they use isotopes to try to date samples. And there's some unique characteristics of all those type of reactions. This here is a decay rate of strontium-90. You'll notice that the half-life is 28.8 years. Here's another sample. Molybdenum-99, 67 hours. So you can see the half-life varies, even though this one's 90 mass, this one's 99. The half-life is almost independent of the mass of the sample. Just because it has more mass doesn't mean it takes longer. Here's a sample and a picture of a sample using here just some shapes to represent this sample. And you've got 100% of the sample, it's kind of like a pie, and over a certain amount of time, 50% go, that's called the half-life. So 50% remain, and then 50% of 50 is 25% of the total of the original, and then 12.5, then 6.25, and then way down here, 3.125. You'll notice that the curve levels out and it goes towards 0, but it never actually reaches 0 until you have that final isotope that decays, and then you would have 0 of the original isotope. Remember, it's decaying into a daughter isotope. So how to get a half-life calculation? Well, you've got iodine-131. It's used to measure the activity in the thyroid gland. If you've got 88 milligrams of I-131 ingested, so your starting amount is 88 milligrams. It's asking how much remains after 24 days. 24 days, and the half-life period is 8 days. So if you take 24 divided by 8, that will give us the number of half-lives, which is 3. So what you need to do is you take your 88 milligrams and you divide it in half. Not once. That would equal 44, but twice. But that's not enough. That will equal 22. Divided a third time, that equals 11 milligrams left. That's all you need to know for half-life calculations. Now, nuclear stability, there are some unique trends and patterns that have been noticed. Certain numbers of neutrons and protons are extra stable. So some things are even more stable, hence less radioactive. If the N neutrons or protons is 2, 8, 20, 28, 50, 82, and 126, these are called the magic numbers. These tend to be incredibly stable. A nuclei with even numbers of both protons and neutrons are more stable than those with odd numbers. So that's a general pattern you can see on the table. All isotopes of the elements after 83, radioactive, of course. And isotopes of TC and PM are radioactive. Those were human created, technetium created in the lab, so it's radioactive. Now, How are they created in the lab? Many of them actually were created by scientists in the laboratory. Glenn Seaborg is one famous scientist that worked at Lawrence Livermore Labs in the University of California, Berkeley. He proposed that there would be a magical island up here where elements with larger masses could be found. One of these elements, element 114, was searched for and discovered by Glenn Seaborg and others. Glenn Seaborg, again, he was alive until 1999. I went to the University of California, Berkeley, and he was my teacher for one of my classes. But his proposals, when he was doing his work, allowed him to discover many of the elements on the periodic table. Element number 106 is named after him, Seaborgium. Element 97 is named after Berkeley, Berkeleyum. 98 is CF, Californium, named after not just our state, but the University of California, Berkeley. And then we have Lawrencinium, 103, named after the Lawrence Livermore Lab. AM, Americanium, number 95, named after America, also discovered at Berkeley. So much of the research in terms of discovery of elements and formation of elements was done by Glenn Seaborg's team as well as many other scientists around the world. UUQ-114 was searched for by these scientists and found based on their properties. Here is a little a widget that shows alpha decay. It's kind of a fun thing to play with if you want to go to the PHET. This site is on the bottom of the page. And this is also radioactive dating. This is how we can date different samples based on half-lives. As I mentioned before, positron emission not tested in Chem 1-2, but this is when you have a beta positive particle being emitted called a positron. In a positron emission, positrons are the antiparticle of the electron. So you have an electron, which has a negative charge, and positron has a positive charge. Now, it's a unique particle because this particle here can also be used in nuclear applications, in nuclear medicine, I should say. Positron emission converts a proton to a neutron. In electron capture, the electron is captured by a nucleus, a light nucleus like carbon. When it's captured, it forms, again, one of the protons combines with the electron to form a neutron. This happens when the nucleus captures that particular electron. Larger isotopes tend to do electron capture rather than positron emission. So carbon-11 is kind of an exception. But mercury, as you can see, does that electron capture. Now, new elements, how are they formed? We should say radioactive decay, nuclear fission, and nuclear fusion. They result in new elements. Is it possible to create a new element? Yes, it is. You have to wait a lot of time for the reaction to occur, or if you take a sample and you say, well, it could decay into gold, for example. One of the samples that could decay into gold is platinum, PT. If it goes through beta decay, you can get gold. So all we need is a lot of platinum and a lot of time, and platinum happens to be more expensive than gold, and we can make gold. This would take more time and money, or lots of energy, as we know from the fusion reactions. So this is a wrap-up of what we talked about today. Fission can be spontaneous for unstable nuclei, or it can be provoked using nuclear bombardment. That's what was done in the nuclear fission examples, the chain reaction as well. So I'd like you to defend this statement, bring this to class based on what you've seen in today's lecture. Talk to you later. Bye.